Hey, what's going on YouTube? Welcome to the next installment in our series building a render engine in C++. In today's tutorial, we will implement a Vertex Shader with an interface very similar to OpenGL's. That way we can do away with the horrific code we're currently using to render objects. If you have not yet seen the first part, which includes an explanation of the concepts used in this video, I highly recommend you go watch that first so you don't get confused. With that out of the way, make sure to like and subscribe for more content like this, and let's just jump into it. Before we begin, I'd like to make a couple changes. So first, open up framebuffer.cpp, and in the recreate function, add clear 0. Now scroll down to the print, and if you add this code and comment out the int color and at your on lines, it'll actually fix a couple bugs. Now what we want to do is go into include, and then open up loader.h, and here we're going to initiate all of these pointers to null pointer so they can be easily freed. So just set positions equal to null pointer, normals equal to null pointer, and UVs equal to, once again, null pointer. Next, we want to have a count for every position, so how many positions there are. We need a normals count for how many normals, and finally a UVs count for the number of UVs. And now we're going to need to initialize those, so if we exit out of that and open up our model loader.cpp, scroll down to the section where we're loading the models, so where it says it's initializing the indices and arrays, model.positionsCount is equal to vertices.size times 3 to start. Model.normalsCount is equal to vertices.size times 3 as well. And then model.UVsCount is equal to vertices.size. This time we want to use times 2. Make sure that's times 2 because there's only 2 vertices or 2 UVs for every vertex. Alright, so now that housekeeping's out of the way, let's start off by adding our first new class, DataList.h. So go into the makefile, add that. And I'm actually going to go ahead and copy the code from an external source for this one, because this is a long class, it's very simple stuff, and it's just used to store data, essentially, and have easy access to the data of different sizes. So it imports every math class, and then it stores a number of floats. And essentially this is just a way of indexing data and storing various different sizes of float data. So get, you can take in a float, a vector 2, a vector 3, and then it will set the data equal to that according to the index location. So you can bind something, well, if you do set location 0 plus 0, each one of these things is going to store an amount of data in a specific location in the array, and you can easily call upon that data at any time. The bind function will allocate a set amount of memory for that. So consider this like a stack but for floating point values, and we're going to use this a lot throughout the code. Links in the description, it's on GitHub. Go ahead and download this and just copy it into your project. Alright, so the first new class is shader.h, well, the second new class. Go ahead and create that new file, if and def include shader.h. We want our include guards, of course. So include shader.h and endif. Now we create a class called shader. Shader class has a couple public fields, a constructor that has a number of uniforms, and this is the first application for the data list. First, make your virtual void, well, let's make it a pure virtual init shader function, and that's just going to initialize all the uniforms. Prepare will be called every frame, make that a pure virtual as well, and finally a virtual destructor. Prepare will be called once per frame, to be clear. Alright, so the private fields. We're going to need our datalist.h, and essentially we're going to be storing a data list for the uniforms. Each uniform has a location, and then you use that location to get and set the uniform values, which will then be called upon during the render process in the shader. So data list, it doesn't have to be a pointer, uniforms. And then let's have a function to get the uniform list as a pointer. So return uniforms. Once that's set up, we're going to need to actually set up the copy constructor for the data list. So once we, well, first of all, let's go into here, and we'll be able to see that we're going to just need to initialize the data list as with an int for the uniform count. And that's all the DataList has in its constructor, as you can see. All right, so now let's go ahead and make a new file. And this is going to be a Vertex Shader. Essentially, we're going to have the Fragment Shader and Vertex Shader inherit from the Shader class. So create the Fragment Shader file as well. And then may as well create some CPP files too, VertexShader.cpp and FragmentShader.cpp. We won't be using these immediately, but we may be using them in the near future. All right, so add the Vertex Shader and Fragment Shader to the set of elements in our make file, and add VertexShader.o and FragmentShader.o. All right, so now hop into VertexShader.h and add our include guards as normal, and add the endif at the end. Now create the class Vertex Shader in here, and inherit from the shader class with public inheritance. And then we want to make sure to include shader.h. Public fields should include the constructor, so add public shader into uniform count, and add the default constructor with the uniform count there. And then just no need to add code for that. Now let's override first let's add the execute function, which takes in a DataList pointer for the attributes, the input attributes, and then it's going to output a DataList pointer attributes out. And then it's going to take an attribute location as well as a vector for the position of the vertex after the calculations are complete. So add in the destructor, and let's go ahead and make it virtual. And also change that m to a comma, so that way it's actually a valid parameter list in C++. All right, so Fragment Shader, we're just going to do the same exact thing. Add the include guards, define include Fragment Shader h, and end if. Class Fragment Shader, inherit publicly from shader once again, and create the public constructor for Fragment Shader, which takes in a uniform count, and then use that to initialize the base class shader. Just like this. And now, once again, let's just create the virtual void execute, but this time we're not going to implement it, just comment it out for now, and we'll take care of that later. And then we can add our virtual destructor once again. And that's all we have to do for the Vertex and Fragment Shader classes for now. And let's just go ahead and include Vertex Shader.h here, and in Fragment Shader.h include Fragment Shader.h. All right, so back into Fragment Shader.h. Let us include our shader.h to make sure that we're not going to have errors. And that's it. So new file here, shaderprogram.h. This is going to basically link a vertex and fragment shader together. And when they're linked, they're going to be able to pass their input and output attributes to each other. They won't share uniforms, but they will be able to communicate correctly. So add the include guards, endif, and class shader program. End it with a semicolon here, and come up to the top, include Vertex Shader.h, and then also Fragment Shader.h. All right, so we'll just put a comment here, binds a Vertex Shader to a Fragment Shader, and that's as simple as that. And we're just going to use it to pass attributes between each other. All right, so public fields, we just need a shader program, which was going to take in a vertex shader pointer VS and the fragment shader pointer FS. Now, when we write our shaders, we're just going to be inheriting from vertex shader and fragment shader. So yeah, let's just leave our initialization list empty before we add the variables. So in private fields, vertex shader pointer VS, and then a fragment shader pointer FS. And then in the constructor, just initialize them, simple stuff. And then call init shader, because this is called once, and this is where it's going to bind the attributes or the uniform values to let it know how big those are going to be. Allocate space for each uniform location. Let's not make these pure virtuals because I don't want to have to write an implementation in the vertex and fragment shader classes. So now come into shader program and prepare. The prepare function is simple. We just call vs.prepare and then fs.prepare. Now there's one more function we need, and that's going to basically allow us to execute the vertex shader. We're just going to call it execute vertex shader and take in a DataList pointer attributes in, the current location, as well as the vector4 reference for the output. And that's just the output of the vertex shader, which is a vector position. Now call vs.execute, give it the attributes in, null pointer for the output attributes for now, we'll change that later. Pass in attribute location and the out vector. All right. Now go into rasterizer. I just want to make a couple changes here. We want a new class called render context. Now the render context is going to take care of the rasterization, but create a layer of abstraction for it. So we can just call render triangles and then give it a VAO and it'll be able to render it. So the constructor, same exact thing as the rasterizer, and in fact it's just a wrapper for the rasterizer constructor. And we'll create a void in render index triangles. Comment it out for now, we'll get back to that. Rasterizer pointer get rasterizer. It will finish implementing this in a second. Once we add the private variables, which is only one coincidentally, and it's called rasterizer. We'll call it R, rasterizer R. In the initialization list, we'll first return the reference to R. Then our initialization list takes in the frame buffer width and the frame buffer height. Don't make it a pointer or a reference pass. That's all we have to do with the raster or with the render context for now. Let's move on to the next class, which is rasterizer.cpp. First of all, in order to avoid bugs, let's go ahead and import atomic and then make each of these variables at the top std atomics. That way it works, it's a little bit more thread safe. Once we put that in, that's really the biggest change we need to make for that right now. But make sure you do make that change because it might not work once you add optimizations depending on your OS. Alright, so the parameters we need for this is a shader program reference shader and a vertex array object VAO. Now a vertex array object is just binding to certain locations all the data that's attributed to a vertex, and I talked about this in the other video as well, which you should definitely go ahead and watch. But we're going to implement this right away, the vertex array object class, which is just going to store a set of buffers for the positions, the normals, and the UVs. And you can of course store whatever data you want in that. So create a new file, call it VertexArrayObject.h, and add your include guards as you would. And once again, end if. Then create the class VertexArrayObject. So essentially we're going to need to store an array of data lists. And this is the input to the shader programs. But first of all, add it to the make file VertexArrayObject.h, and we're going to make a CPP file too. So add VertexArrayObject.o as well. Now in here, we want our public variables. Well, first of all, let's create VertexArrayObject.cpp before we forget. And include that at the top here, the VertexArrayObject.h. So the public fields, we're going to have a constructor VertexArrayObject, which is going to take in an integer for the number of buffers. We'll call it buffer count. And this is just going to be the number of arrays of floats that we need to pass to the shader. So in our case, it will be 3, because we need normals, positions, and UVs. So now add the private members, which is a int buffer count, as well as a DataList pointer for the buffers, and an int pointer for the index count, and then, well, actually an int pointer for indices, since not index count. And then index count is just a normal integer. Now the DataList is going to store the buffers themselves, but an int pointer will be separate for the indices. And using our data list, we'll be able to easily get attributes from the buffer. So initialize buffer count with buffer count, initialize buffers with a new DataList pointer of buffer count size. The index buffer should be set to null pointer to begin with because you don't have to initialize that. And now loop through every single buffer and initialize it to set it equal to null pointer to begin with. Now, what we're going to do here is void buffer data. Now this is a function that you call whenever you add data to the buffer. So you give it an attribute location, a float pointer data, an int count, and an int steps per vertex. So that will essentially bind data to the data list depending on the size being the number of steps per vertex. So if it's 3, it'll bind 3 to each index of the thing. Buffer indices takes in an int pointer indices, an int count, and that's all you need. Let's go ahead and make a destructor here. Vertex array object. And then have an int pointer get indices. And then return the indices there. It's pretty simple. Make sure that says vertex array object and not vertex object. And we'll implement that in the CPP file. Return index buffer as well. DataList pointer get buffer data. Return buffers. And now we want to be able to get the size. So int get buffer count. And that will return just the buffer count. So just a bunch of getters and setters here, not even setters. Get index count will return index count. What a shock. All right, with that out of the way, we can start with the implementation. So go into VertexArrayObject.cpp and initialize, well, first implement the destructor. We're just going to need to loop through every buffer and make sure that we delete it. So loop through buffer count and go through delete buffers sub I, and at the end, delete array buffers. All right, so implement void vertex array object buffer data. Take in an int attribute, float pointer data, int count, and int steps per vertex, just like we did in the declaration. And then if the buffer that we're targeting is equal to null pointer, then we're good to go. Otherwise, we have to free the data and then actually add it again. So call delete buffers subattribute. Buffer subattribute equals null pointer, and then recursively call buffer data with the same exact parameters that we passed in. All right, so now when we actually buffer the data, we just need to copy it into the array as given the size, the steps for vertex. So initialize the new array and then do a float pointer I is equal to data. I is less than data plus count, and I plus equals steps per vertex. So if it's 3, it's going to copy 3 floats per step. Buffers subattribute dot bind and give it I, comma, steps per vertex. So that's the number, well, we're giving it the array and the number of floats to copy in. The next one to create is buffer indices. Take in the int pointer indices followed by the int count. And once again, we need a recursive call in case the indices are already initialized. So set up that same if condition, then otherwise delete index buffer and set it equal to null, and then recursively call buffer indices with the same exact parameters. Luckily, the copy is pretty simple here. Index buffer equals new int count, and then loop through, first initialize index count equal to count, and loop through each and every index and set, we'll actually call that index count, not whatever I had before. Index buffer sub I is equal to indices sub I. Simple as that, and we've copied over all the indices. All right, so hop into rasterizer.h, and now that we have the vertex array object, we can actually implement render index triangles. First, we're going to want to include vertex array object and include shader program.h, and that's all we need. So now let's go ahead and implement this in rasterizer.cpp. We're going to need to scroll all the way down to the bottom. Right at the very end of the file, we're going to initialize void render context : render index triangles, pass in all the parameters, which is just shader program reference shader and a vertex array object reference VAO. Now this is pretty simple. Just call prepare on the shader once per render, and then create 3 vertices, v1, v2, and v3. Now add in void vertex shader, pass in, this is just going to call the vertex shader on each vertex, and give it the VAO and then the int index that we're currently looking at, as well as the vector4 for the output. Now this is a simple function, shader.execute shader, and give it the VAO.get buffer data, the attribute location as the vertex index, as well as the out shader. So it's just a wrapper function that'll make it a bit easier to look at. All right, so same as what we did before last week. We do for int I equals 0, I is less than VAO.index count, and then I plus equals 3. So we go through each and every third index. And then we call the vertex shader function with the shader, the VAO, the indices sub I plus 0, and then the output vector, which is v1. And we do this 3 times. 1 for offset by 1, 2, and then we initialize, or we pass in v2 and v3. All right, so once it calls the vertex shader in those, it transforms the point. So we just need to call rasterize triangle with a new vector 2 for each and every transformed vertex. So let's go ahead and make those happen here. And this is just v1.x. Now remember we have to do a z divide, so divide that by v1.z. And then give it v1.y, also divided by v1.z. We did that same exact thing in many tutorials ago, so you know what this is doing. v2.y divided by v2.z. v3.x divided by v3.z. And then once again v3.y divided by v3.z. And that's all we have to do, so at least in this class. Now let's go into main.cpp here and actually start to use this code. It's very simple interface to use. And we don't have to link any OpenGL libraries as well, so it's very simple. Replace the rasterizer with a render context pointer. And then we're going to want to include our shader program to start. And we're going to want to create our shader program that we're using for this. So call it shader, and just give it null pointer for now. It won't actually work with this, but add it in for now. And then instead of rasterizer.clearFrame, we need renderContext.getRasterizer.clearFrame. And we just need to replace every reference to rasterizer with render context. So render context is equal to new render context here instead of rasterizer. And then go ahead and do render context.getRasterizer instead of just rasterizer for this. And then present frame, same exact thing. Swap buffers, same exact thing. And we're good to go. All right, so at the end, just delete render context instead of rasterizer. All right, so the last thing to do is render context.getRasterizer.rasterize triangle. Now this is the same code we did before with the disgusting looking transformations. This is what we're going to fix here. So create a vertex shader VS and give it 1,000 uniform locations, and fragment shader FS with 1,000 uniform buffer as well. And then give it VS and FS the address of both of them, and that's it for the shader program. We can see it builds, and when we run it, it does the exact same thing as last week. All right, so down here, you can see we're doing all this disgusting code in order to make this work, and we're shorthanding this by making a much better interface. First, let's go into camera.h and add 2 functions here. We want inline matrix 4x4 get projection, or actually first let's get view matrix and return view matrix. The other one is a matrix 4x4 get projection matrix and return proj matrix. And those are just what we're going to be using to calculate this stuff instead of passing it through on this area and calculating the final matrix here. We're going to be doing that in the shader, the Vertex Shader. So we can start by creating a VertexArrayObject model VAO, and this is where we're going to store all the data for the model once we've loaded it. Give it 3 buffers because that's what we need for the positions, normals, and UVs. So right after we've loaded the model, it's time to pass all that data to the buffers. So call buffer data and give it the attribute location 0 and give it model.positions count for the number, and the steps for vertex is 3. Now we're going to buffer the UV data at index 1 and give it the model.UVs count, and 2. In model.VAO, buffer data at the attribute location 2, we give it model.normals count, and 3 as a step. Now finally we need to buffer the indices. So call buffer indices, model.indices, and model.index count. Who'd have thought? Alright, so that's loading all the data from the model into the VAO, which will be then used to rasterize the triangles for the object. Delete everything here because we no longer need it. Don't delete the entire function, but we can get rid of the PV matrix too. Just every call to rasterizing the triangles one at a time. Now, of course, if we run this right now, nothing will happen. You can also get rid of the transform vertex function. Now, the simple interface is to set up the uniforms, then render the object using the shader and the VAO. And that's what we're going to do here when we create our first shader, basic shader.h. And this shader is going to do the transform exactly the same as what we've been doing before, but it's going to be doing it in a shader rather than separately. Basic vertex shader, publicly inherit from Vertex Shader here, and then give it the public function, the public constructor, basic vertex shader, which doesn't take in anything, and just give it a buffer of 1000 for a basic shader. So in init shaders, this is once again where we bind the uniform locations, and prepare, this is where we set up the long calculations that we don't want to do each vertex. And then our execute function, which takes in the DataList pointer in, the output the attributes, as well as the attribute location, and the vector 4 for the output vector. Very simple stuff. So we need an int for the location of the projection matrix, an int for the location of the view matrix, and an int for the location of the transformation matrix. Now you use those locations to set and get uniform values. In shader, we initialize init projection matrix with uniforms.bind, because that will allocate space in the buffer. Give it the projection matrix so it knows the size. And we're going to initialize those variables in a second here. We're going to want to include Vertex Shader.h, and we're also going to want to include Fragment Shader.h. So create the matrices, projection matrix, view matrix, and finally transformation matrix. And then the last matrix is the final matrix, which we're going to calculate and prepare. Location view matrix is equal to uniforms.bind, and pass in the view matrix, just allocate 16 floats of space for that. And then the location transformation is binding the transformation. So at the top here, include basic shader.h. And we actually need to make these members private in Vertex or in shader.h. So make that protected instead of private. So now that those locations are bound here, location projection matrix is 0, view matrix is 1, and transformation is 2. You're going to want to get the uniform at the location projection matrix and give it the projection matrix reference. And we're going to want to do the same thing with the view matrix, and once again, the same thing with the transformation matrix. And we're going to be setting these vectors from the class where we call the render. So once you get all those values, you just calculate final matrix as projection matrix times view matrix times the transformation matrix. Now in execute, we just load in the attribute locations, calculate the final vertex position as the return. So we need a vector 3 for the pose and the normal, and a vector 2 for the UV. Now we get these locations by doing attributes in sub 0, because we bounded at that location. We do .get attribute location, the current attribute location, and then you give it the position as the output. And then at position 1 is the UV, so give it attribute location, and then, well, actually the UV, not the normal. And that'll get 2 floats for the UV. So attributes in sub 2, this is the normal, and give it the norm as the output there. And that's how you get your attribute locations. And we bound it 0, 1, and 2 because the positions are at attribute location 0, the UVs are at attribute location 1, and the normals are at location 2. Okay, so to calculate the final vertex position, we do output is equal to final matrix multiplied by vector 4, pose.x, pose.y, pose.z, and a 1. And that's it. The basic fragment shader or vertex shader is finished. So if we include that here, give it basic shader vs, and then instead we need to give this as a vertex shader pointer vs. Now we'll worry about the fragment shader next tutorial. So here's where we set the uniforms. We do get uniforms.set, we give it vs.location projection matrix, and you give it the camera.get projection matrix. And then you can get the uniforms again, and this time set the vertex or the view matrix. So you use the location of the view matrix in the thing, then you give it the camera.get view matrix, and finally vs.getUniforms.set, give it the location of the transformation and the transformation matrix, which we calculated here. Let's make a change here and move this back to 2 units. And now to render the object, all you have to do is do render context.render index triangles. You give it the shader program and the VAO, so the model VAO. And that's all you have to do to render the model here. So if you see make run, and we still have the spinning bead just like we had last tutorial. Fantastic. Let's quickly just change the axis of rotation here, move it back a little bit less so we can see the effects once more, and give it one more run. Look at that, that's just beautiful. We've essentially just taken the same system as before and made it more abstract, so now it's much easier to work with. In the next tutorial, we can cover all sorts of stuff like lighting, we can cover texture mapping, we can cover just everything. But first we're going to need to actually set up the fragment shader, which will probably be a tutorial on its own, and then after that we'll work on the other stuff. Alright, so I hope you learned, I hope you enjoyed, and I will see you next time.